Welcome back. Let's practice finding torsion of space curves. All right, so here's our first example. We want to find the torsion for this vector function. R of t is equal to ti plus sine tj plus cosine tk. All right, and what it means for us to find the torsion of this vector function, since we're not given a specific value of t where we want to find the torsion, what this means is we just want to find a general expression that represents the torsion of this space curve at a particular value of t. And so in order to find that, in order to find a general expression of the torsion, we will use the following formula. The torsion, represented by the Greek letter tau, is equal to the cross product of r prime of t with r double prime of t, and then you take that cross product and take the dot product of it with r triple prime of t and divide by the magnitude of the cross product between r prime of t and r double prime of t, where you square that magnitude. And you could view that numerator, if you'd like, as a triple scalar product, right? You have a cross product of two vectors that you are then taking the dot product with another vector. Okay, so that's the formula we're going to use. That's how we're going to calculate torsion. And so to get started here, we have to actually find the first, second, and third derivatives of our vector function. So let's do that. Starting with the first derivative, r prime of t is equal to the derivative of these components. The derivative of t is 1, the derivative of sine is cosine, and the derivative of cosine is negative sine. So we have I plus cosine t j minus sine t k. All right, then let's take the second derivative, r double prime of t. The second derivative will have components that are the derivative of the first derivative. The derivative of 1 is 0, so we will have 0i, and then the derivative of cosine is negative sine, and the derivative of sine is cosine. So we have minus sine t j minus cosine t k. All right, and then we need to take the derivative one more time. So we'll have r triple prime of t. This is the third derivative. The derivative of 0 is still 0, so we have 0i. And then the derivative of sine is cosine, so we have minus cosine tj. And the derivative of cosine is negative sine. So that negative will cancel out with this negative, leaving you with positive sine t k. All right. So now we have the first, second, and third derivatives of our vector function, which we can now use for our torsion formula. And so what we want to do next is take the cross product of the first and second derivatives. So let's set that up now. We're going to take r prime of t and cross it with r double prime of t. So you want to set up a 3x3 matrix where the first row is I, j, and k. By the way, I did mention that this numerator is a triple scalar product. Technically, you could calculate this as a triple scalar product. You could use a matrix where the first row is the components of r prime of t, the second row is the components of r double prime of t, and the third row is the components of r triple prime of t, where you could then calculate the triple scalar product by doing the cross product calculation on that matrix, where instead of I, j, and k, you just have the components of that first vector that you're multiplying by each of the 2x2 determinants that you calculate. Okay, the reason I'm not doing that here is because we do have to take the magnitude of the cross product between these two vectors. And so it's going to be more convenient to just calculate that cross product so that we can find its magnitude more easily. And then it's not too difficult to go back and calculate the dot product between this cross product and the third derivative. Okay, so this is the way I prefer to do it. Again, you could calculate the numerator as a triple scalar product, but my preference is just to do the cross product and the dot product separately. Okay, so now setting up the matrix, the middle row will be the components of r prime, and the bottom row will be the components of r double prime. So for r prime, that's 1 cosine t and negative sine t, and for r double prime, that's 0, negative sine t, and negative cosine t. All right, so 1 cosine t, negative sine t, and then 0, negative sine t, negative cosine t. All right, now calculating this cross product, start by covering up the I column, then calculate a 2x2 determinant. Cosine t times negative cosine t is negative cosine squared t, and then you want to subtract negative sine t times negative sine t, which is positive sine squared t. So we have negative cosine squared t minus positive sine squared t. That's multiplied by I. Then you want to subtract the j term. So cover up the j column, calculate another 2 by 2 determinant. 1 times negative cosine t is negative cosine t minus negative sine t times 0, which is 0. So you're subtracting negative cosine t, but those negatives would cancel out. So you just have plus cosine t times j. So I'll write plus cosine t j. And then for the k term, cover up the k column, and then 1 times negative sine t is negative sine t minus cosine t times 0, which is 0. So you have minus sine t k. All right, now, before we do anything else, I do see that we can simplify the x component here. If you pull out a negative 1 from these two terms, I'll do that here real quick. Watch what happens. If you pull out a negative 1, you'll have a negative quantity of cosine squared t plus sine squared t, and cosine squared t plus sine squared t we know is equal to 1 from the Pythagorean identity for sine and cosine. So this is equal to just negative I plus cosine t j minus sine t k. All right, that right there is the cross product between the first and second derivatives. So now that we have that cross product and it's fully simplified, we can do everything else that we need for this formula. In particular, we need the magnitude of that cross product, and we need to take the dot product between that vector and the third derivative. So let's start with the magnitude. The magnitude of the cross product between r prime of t and r double prime of t will be equal to the square root of the sum of the components squared. So we have negative 1 squared, which will just be 1, plus cosine t squared. So you get cosine squared t, and then you have plus negative sine t squared, which will be plus sine squared t. Okay, squaring negative sine gives you positive sine squared t. All right, now simplifying, once again, cosine squared t plus sine squared t from the Pythagorean identity, we know that that is equal to 1. So the magnitude is just equal to the square root of 1 plus 1, which is the square root of 2. Okay, so now the only thing left to do before we can calculate torsion is to take the dot product of our cross product vector with the third derivative r triple prime of t. So let's do that here. I'll just put it right into the setup for our torsion calculation. We're going to have that torsion is equal to the numerator where we're taking that dot product. So we're going to take the sum of the product of corresponding components. So we'll start with the x component of our cross product. We'll take negative 1 times the x component of the third derivative, which is 0. So we get negative 1 times 0, and then you'll add that to cosine t times negative cosine t. So we have plus cosine t times negative cosine t, and then you want to add that to negative sine t times sine t. All right, we're just multiplying the z components. So we have negative sine t times sine t. And then in the denominator, we have the magnitude of the cross product squared. We found that the magnitude of the cross product was the square root of 2. So we have the square root of 2 squared. Now simplifying, negative 1 times 0 is 0. Cosine t times negative cosine t will be negative cosine squared t. And then you're adding that to negative sine t times sine t, which will be negative sine squared t. So the torsion here is negative cosine squared t minus sine squared t divided by the square root of 2 squared, which is just 2. But then in the numerator, just like we did for the x component of our cross product, there's a common factor of negative 1 that can be pulled out. And then you have cosine squared t plus sine squared t, which we know is equal to 1 from the Pythagorean identity. So this just reduces to negative 1 divided by 2, or negative 1/2. That right there is the torsion, or the expression for torsion, of this space curve. And you'll notice that it is constant, which means that this space curve is constantly twisting with the same intensity. It's never twisting more or less at any point. It always has the same amount of twisting that we call torsion. All right, and so that's it for this example. We have now found the torsion for this space curve. So let's take a look at another example. Here we want to find the torsion of this vector function. R of t is equal to t squared times I plus t cubed times j plus t to the power 4 times k. All right, and so we're going to go through the same exact process that we did in the previous example. We're going to use the same exact formula that torsion is equal to the cross product between the first and second derivatives, dot product with the third derivative, and then you divide by the magnitude of that cross product squared. Okay, so we're going to start by finding the first, second, and third derivatives of our vector function. The first derivative, r prime of t, is equal to the derivative of these components, where we just need to use the power rule for derivatives a couple times. We'll get 2ti plus 3t squared j plus 4t cubed k. All right, now we'll take the second derivative, so r double prime of t is equal to 2i plus 6tj plus 12t squared k. All right, I just took the derivative of each of the components of the first derivative to get these components. And then finally, we need to find the third derivative, so r triple prime of t is equal to the derivative of these components. 2 is a constant, so we will get 0 for that. We have 0i plus 6j plus 24t times k. All right, and so there we have the first three derivatives of our vector function. And so now that we have those derivatives, let's work on the rest of this formula. We need to take the cross product of the first and second derivatives. So let's set that up. We're going to have r prime of t cross r double prime of t. So setting up the 3 by 3 matrix, we have I, j, and k. And then the second row will be the components of r prime of t. So that's 2t, 3t squared, and 4t cubed. Let's write that in there. 2t, 3t squared, and 4t cubed. And then the bottom row will be the components of the second derivative. So that's 2, 6t, and 12t squared. So I'll write those in. 2, 6t, 12t squared. All right, so now let's calculate the cross product, beginning with the I term. Cover up the I column. 3t squared times 12t squared minus 4t cubed times 6t. 3t squared times 12t squared will give you 36t to the power of 4, and then we are subtracting 4t cubed times 6t, which gives us 24t to the power of 4. All right, that's multiplied by I. Then we will subtract the j term, covering up the j column. 2t times 12t squared minus 4t cubed times 2. 2t times 12t squared is 24t cubed. So we have 24t cubed minus 4t cubed times 2, which is 8t cubed. So that's multiplied by j, and then we have plus the k term. So cover up the k column. 2t times 6t minus 3t squared times 2. 2t times 6t is 12t squared. So we have 12t squared minus 3t squared times 2, which is 6t squared. All right, so that's multiplied by k. Now we need to simplify, and nicely enough, each of these components contains terms that are like terms, so we can combine them pretty easily here. 36t to the power 4 minus 24t to the power 4 will give us 12t to the power 4, so that's multiplied by I. Then you want to subtract the j term. 24t cubed minus 8t cubed gives you 16t cubed, but we are subtracting it, so we have minus 16t cubed times j. And then finally for the k term, 12t squared minus 6t squared is 6t squared, so we have plus 6t squared times k. All right, so that's the cross product vector. Now let's calculate its magnitude. So we'll take the magnitude of the cross product between r prime of t and r double prime of t. So this will be equal to the square root of the sum of these components squared. 12 squared is 144. T to the power 4 squared is t to the power of 8, because you'd multiply the exponents of 4 and 2. So you get 144 t to the power of 8, and then you'll add that to negative 16 t to the power of 3 squared. And negative 16 squared is positive 256. So we have plus 256, and then t cubed squared is t to the power of 6, and then plus 6t squared squared gives you 36t to the power 4. All right, now we can simplify this. There is a common factor that we can pull out of each of these terms. Specifically, the factor is 4t to the power 4. all these constant multiples have a common factor of 4 that can be pulled out, and then t to the power of 8, t to the power of 6, and t to the power of 4 all have a common factor of t to the power of 4 that can be pulled out. So this would be equal to the square root of 4t to the power of 4 times 36t to the power of 4 plus 64t squared plus 9. Okay? That's what you're left with from these terms after pulling out this common factor. Now, the reason we did that is because we can take the square root of 4 and t to the power of 4. That will give you 2t squared times the square root of these terms. And so you have 36t to the power of 4 plus 64t squared plus 9. And that's about all we can do. These three terms can't be simplified any further. I don't believe you can factor them, and even if you could, I wouldn't really bother. There's no need to. You can work with those terms as they are. It's not like we need to integrate that or something, right? In the past, we tried to simplify our magnitudes as much as possible because we would have to integrate them for the arc length parameter or something like that. In this case, we don't have to worry about that, so you don't have to simplify the magnitude as much, but I do believe in this case that it is in its simplest form anyway. But now that we have that, the only thing left to do is to take the dot product between our cross product vector and the third derivative of our vector function. So let's work on that next. In fact, I'm going to calculate it right into our torsion formula, just like I did in the previous example. In the numerator, we will have the dot product between the cross product and the third derivative. So we're going to take the sum of the product of corresponding components. So starting with the x components, 12t to the power 4 times 0. We know that's going to be 0, but I will write it out anyway. We have 12t to the power 4 times 0 plus the y components multiplied together. So we have negative 16t cubed times 6. So negative 16t cubed times 6. And then we have plus the product of the z components. So we have 6t squared times 24t. All right, so 6t squared times 24t. All right, and then in the denominator, we will be squaring the magnitude of the cross product. And so we have 2t squared times the square root of 36t to the power of 4 plus 64t squared plus 9, and that whole quantity is squared. All right, now simplifying, the torsion will be equal to the simplification of this expression. Anything times 0 is 0, so we can cross that out. Then negative 16 times 6 is negative 96. So in the numerator, we have negative 96t cubed, and then you're adding 6t squared times 24t. 6 times 24 is 144. T squared times t is t cubed. So we have plus 144t cubed. Those are like terms, which is pretty nice. But then that is divided by this denominator squared. Squaring 2t squared gives you 4t to the power of 4. And then you're squaring this square root. So you're just left with the terms inside the square root. So you're multiplying by 36t to the power 4 plus 64t squared plus 9. Okay? Now, like I said earlier, in the numerator, we have like terms. They both are t cubed terms, so you can add the coefficients. Negative 96 plus 144 is 48. So I'm just going to change that right now. In the numerator here, we have 48t cubed. And then we have some nice cancellation that occurs to finalize our answer. 48 divided by 4 is 12. So this 4 is gone and this becomes 12. And then t cubed cancels out with 3 of these t's. So that's gone and this becomes t to the first power. All right, so our final answer here is that torsion is equal to 12 divided by t times 36t to the power 4 plus 64t squared plus 9. That right there is the expression that represents the torsion of this space curve. All right, so if you want to know the measurement of torsion at a specific point along this curve, you just need to know the value of t for that point and then plug that value of t into this expression and you'll get the measurement of the torsion. Okay, so unlike our previous example, the torsion here is not constant. There are t's in the expression, so it will depend on what value of t or what point you are at along the curve. Okay, and so that's it for this example. Let's take a look at one more for this video. Hey there, real quick, before we take a look at the next example, If you find my tutorial videos here at JK Math to be helpful, then I'd like to invite you to join my membership site, JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. So if you are interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Alright, so here's our last example. We want to find the torsion of the curve at t equals 0 for this vector function. R of t is equal to e to the power of ti plus e to the power of negative 2tj plus e to the power of 3tk. Alright, so unlike our first two examples, this time around we're looking for a specific value of the torsion at a point along the curve. Alright, we're not looking for a general expression that represents the torsion at any point along the curve. We are looking for one specific value of the torsion, and that is at t equals 0. So the way we go about this problem can be a little bit different, and let me explain what I mean by that. We're still going to use the same formula, that being this formula right here that we've been using so far, but we don't have to work in terms of t. What we can do is use this formula, but where all of these vector functions are evaluated at t equals 0. All right, in other words, what I mean is we can find the torsion at t equals 0 like this. In the numerator, we'll have r prime of 0, or the cross product of that vector, with r double prime of 0, and then you take that cross product and take the dot product of it with r triple prime of 0. And then in the denominator, you'll have the magnitude squared of that cross product. So you'd have r prime of 0 and then r double prime of 0. Since we don't have to find the general expression for the torsion, we just want a specific value, there's no reason to calculate the general expression in terms of t. We can make the process quicker for ourselves by working entirely in terms of these vector functions when t equals 0. Alright, so we're going to find the first, second, and third derivatives in terms of t, but then to make things nice, we're going to plug in t equals 0 right away into each of those derivatives before we use them to calculate a cross product, the magnitude of that cross product, and take the dot product between the cross product and the third derivative. Okay, it's going to be a lot nicer if we just work in terms of the constant vectors that we'll get from plugging in t equals 0. All right, so let's start by finding the first, second, and third derivatives. So starting with the first derivative, r prime of t is equal to the derivative of these components. Now the derivative of e to the power of t is itself, so we have e to the power of t I, that does not change. And you might think the same thing for the y component, but remember, when the exponent is not just t, then you have to be careful. You want to make sure to multiply by the derivative of that exponent. When you're just working with e to the power of t, the derivative of t is 1, so it doesn't matter. The chain rule really isn't being applied, or I guess it is, but we don't care because the derivative of t is 1. But in this case, the derivative of negative 2t is negative 2. So you need to multiply by that derivative. So really, instead of having plus the j term, we will have minus 2 times e to the power of negative 2t. You keep the same exponential function, but multiply it by the derivative of that exponent. Okay, and then we'll do the same thing for the z component. The derivative will not just be e to the power of 3t, it will be 3 multiplied by e to the power of 3t, because the derivative of 3t is 3. So we have plus 3 e to the power of 3t times k. All right, and so that's the first derivative. Now let's find the second derivative, r double prime of t. We're going to be taking the derivative of these components. Once again, e to the power of t. Its derivative is itself, so we have e to the power of t times I. Then we need to take the derivative of this component, and so it will just be that exponential function, but we do need to multiply again by the derivative of the exponent. So we're multiplying by another negative 2. So that results in positive 4 e to the power of negative 2t j. And then once again, for the z component, we will need to multiply by another 3. So we get plus 9 e to the power of 3t k. All right, Now let's move on to the third derivative. We'll have r triple prime of t is equal to e to the power of ti. That derivative does not change. But then for the y component, we do need to multiply by another -2. So we'll have minus 8e to the power of -2t times j. And then for the z component, we will multiply by another 3. So we have plus 27e to the power of 3t k. All right, so now at this point, obviously you could go about it the way we did in the first two examples. You could find the general expression in terms of t for the torsion and then plug in t equals 0, but I'm going to take a little shortcut here. Let's evaluate these three vectors at t equals 0 and then use them for this calculation. Okay, you could certainly do it in terms of t, but the cross product between the first and second derivatives could get a little messy because of these exponential functions. You could certainly do it, it's not that bad, but it's going to be way easier if we just work with our vectors evaluated at t equals 0. Okay, so let's plug in 0. We'll have r prime of 0 is equal to each of these components evaluated at 0. And notice that in each case, the only t's present are in the exponents of e. And so when you plug 0 in for t, that exponent is just going to be 0. This one's 0, 0 times -2 is 0, 0 times 3 is 0. So you just have e to the power of 0 in each case, which is equal to 1. So you have 1 for each of those exponential parts multiplied by whatever the coefficient is. So for the x component, you just get 1, so we have I. For the y component, you'll just get -2, so we have minus 2j. And then for the z component, you'll just get 3. 3 will be multiplied by 1, so you just get 3k. All right, and then a very similar thing will happen for the second derivative. R double prime of 0 will be equal to each of these components, but plugging in 0 just results in an exponent of 0 for each of those e's, so they just become 1 multiplied by the coefficient. So we get components of I plus 4j plus 9k. And then for the third derivative, r triple prime of 0 is equal to plugging 0 in for t, and all of those exponential parts just become 1, so you get I minus 8j plus 27k. All right, so now we have much easier vectors to work with for calculating torsion at t equals 0. They're all constant terms, which is going to be very nice when we go to do our cross product and dot product. Speaking of which, let's do those two calculations now, starting with the cross product. We're going to take r prime of 0 and cross it with r double prime of 0. So setting up the 3 by 3 matrix, we have I, j, and k. The middle row will be the components of r prime of 0. So that would be 1, -2, and 3. So let's write those in. 1, -2, 3. And then the bottom row will be the components of r double prime of 0, which are 1, 4, and 9. So we have 1, 4, 9. All right, now let's calculate the cross product here. For the I component, cover up I, -2 times 9, minus 3 times 4, which is 12. So we have -18 minus 12. That's equal to -30. So let's erase that and write -30i. We then subtract the j term, cover up the j column. 1 times 9 is 9, minus 3 times 1, which is 3. And so you have 9 minus 3, which is 6. All right, so we have minus 6j. Then finally, we have the k term. Cover up the k column. 1 times 4 is 4, minus -2 times 1, which is -2. So you have 4 minus -2, which is 4 plus 2, which is 6. So we just have plus 6k. So that's our cross product. Now let's calculate the magnitude of that cross product. So we're taking the magnitude of the cross product between r prime of 0 and r double prime of 0. So we're going to take the square root of the sum of these components squared. So that results in -30 squared plus -6 squared plus 6 squared. -30 squared is 900, and -6 and 6 squared are both 36. So let's just rewrite that right in this step here. We have 900 plus 36 plus 36. Okay, and 900 plus 36 gives us 972. All right, now I think you could simplify that. I think 972 has a factor that is a perfect square. but I'm going to hold off on that because we do end up squaring this magnitude in the formula. So this will just end up being 972 in that denominator, okay? But now we're almost done. We just need to set up our torsion calculation, and in doing so, take the dot product of the cross product vector with the third derivative evaluated at 0. All right, so let's do that. I moved our cross product vector over here, and its magnitude is right down here. For our torsion at t equals 0, we will have that this is equal to that triple scalar product in the numerator, or the dot product between the third derivative at 0 and our cross product. I'll do that in just a second. I want to start by just writing in the magnitude of our cross product squared. So we have the square root of 972 squared. But then in the numerator, let's take the dot product of our cross product with the third derivative. We'll start by multiplying the x components. Negative 30 times 1 is negative 30. So we have negative 30 plus the product of the y components. So we have negative 6 times negative 8. So I'll write down negative 6 times negative 8. And then adding the product of the z components, we have 6 times 27. So plus 6 times 27. All right, now simplifying, the torsion is equal to negative 30. And then negative 6 times negative 8 is positive 48. So we have plus 48 plus 6 times 27, which is 162. And then that's divided by 972. But now negative 30 plus 48 will give you positive 18. And then 18 plus 162 gives you 180. All right, so this is equal to 180 divided by 972. And then both 180 and 972 have a common factor of 36. So dividing out that factor of 36, you are left with that the torsion is equal to 5/27. All right, that is what it simplifies to. That is the value, the specific value of the torsion at t equals 0 on this space curve. All right, so hopefully you can see that that work that we did was a lot simpler than it would have been if we tried to find the torsion in terms of t first and then plugged in 0, since we didn't need that general expression. Evaluating our three derivative vectors at that specific value of t made our work simpler and saved us a lot of time. Okay, so that's my recommendation on how to go about these problems where you need to find torsion, but not a general expression, just a specific value for a point on the curve. But with that, that is it for this example, and this was also the last example for this video. But if you want to work more with torsion, I have more videos available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. I'll also have the link for that in the description of this video. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.